All right, so let's calm down and start on the new material. Where is everybody?
Crying at home. Majority of them.
All right. So on, I guess it was last Thursday, we started talking about reactivity of amines. This was after our reductive amination section. You guys should be pretty comfortable with reductive amination at this point. But with acylation, we said that acylation is very straightforward. We've already seen it before. And the reason that it's useful synthetically is if we tried to brominate aniline, we'd end up over-brominating aniline. Anilines are too strong of an activator. So in this case, what we can do is acylate the amine, then brominate. We've turned a strong activator into a weak activator. And then we can take our acyl group and then hydrolyze it off to get back to our aniline. So this is synthetically useful for some of the chemistry that we've already seen. All right, so let's continue on and talk more about reactivity of amines. This next one is a name that's familiar to us, or hopefully is familiar to us. This is called the Hoffman Elimination. It'll be all right. All right, Hoffman Elimination. We saw this in first term, actually, so let's take a look back at first term. In first term, we said if we have an alcohol and we treat this with strong acid, we can dehydrate it, right? And we can get to our alkene. So the question is, amines are pretty similar to alcohols. Can we do the same sort of reaction? So let's say we've got an amine that looks like this. Is it possible to do this reaction? That's the big question. I mean, inherently you would say, well, let's just throw acid at it and do the same sort of reaction. But in this case, it doesn't work the same as alcohols. The amines aren't great leaving groups like an alcohol is under acidic conditions. So what we have to do is figure out how to convert this amine into a better leaving group. Nope, there's actually a trick. So I'll call this LG for leaving group. So let's take a look at the mechanism. And the key for turning this nitrogen into a good leaving group is to actually get it charged, just like with alcohol. The alcohol, we protonate it, the oxygen has a positive charge, and then it turns into a good leaving group. What's another way of giving a positive charge to a nitrogen? Besides a hydrogen? Yeah, we can alkylate it. So the mechanism for the Hoffman elimination starts with alkylation. So what we do is we take methyl iodide and we use quite a bit of methyl iodide. And so when we do this, we can do that exhaustive alkylation where the nitrogen reacts 3 different times with that alkyl halide. Now that nitrogen's a good leaving group, but there's one problem. In this reaction, we're forming a salt. And the salt, in this case, is going to be the iodide salt. Iodide isn't a very good base, right? It's a very, very poor base because it's a conjugate base of a strong acid. So the trick for this is we need to convert iodide into a better base. So what we do is we react this with silver oxide. Silver oxide is very, very reactive with halides. So what ends up happening is you form silver iodide. Let me actually slide over here. And this silver iodide is completely insoluble. It will precipitate out. And I'm going over this with my Chem 110 students right now. We've got a nonmetal oxide, and it's in water. Will this form an acid or a base? Acid. Wrong. Base.
Oh,
because I knew it. Sorry. It's hard not to laugh at Kareem sometimes. All right, so we're going to convert this iodide to hydroxide. And we've got these beta protons. So this hydroxide can come, grab a beta proton, clamp down, and kick off our leaving group.
It's about time, Eddie. I'm recording to hear that.
All right, and when we do this, we get our alkene, and then our byproduct is going to be trimethylamine and water. So we're able to drive an elimination reaction by turning our amine into a good leaving group just simply through over-alkylation. What sort of elimination reaction is this, just to practice? Is it E1? Is it E2? It's E2, which means it's completely concerted, right? So with E2 reactions, what's the other defining feature besides being concerted? With the proton we're grabbing, what does it have to be? So this will be a review. What position does this proton need to be in?
It has to be beta.
Has to be beta to our leaving group. And there's another key feature. Anticoplanar. So we also have to look at this, and we have to remember that this proton must be anticoplanar for E2. Okay, so now let's take a look at the regiochemistry for this reaction. So let's take a look at this compound. I'll give you guys an example one. Oops, sorry, this should be our over-alkylated amine. Are we going to get this alkene out, or are we going to get that alkene out? Does anybody have an initial guess?
Depends on your base, wouldn't it?
Let me draw this a little bit more clearly. Raise your hand if you think the left alkene. Raise your hand if you think the right alkene. Raise your hand if you remember what Hoffman product means. Which one's our Hoffman product? The one on the right. So if we're doing Hoffman reactions, we're probably going to get the Hoffman product, the one on the right. If we remember the name of this alkene, what is this called? Zaitsev product. So even though this is more thermodynamically stable, we're actually going to get the Hoffman product out because it's a Hoffman elimination reaction.
That's always the case.
Yep, and we'll talk about why this is the case. So in this case, this is Zaitsev, and it's not observed.
Why?
So let's talk about why. All right, since we're going to take a look at this, I'm going to color code some protons. All right, so let's look at this set of beta protons. And then for this one, it doesn't really matter the stereochemistry. And I'll call these ones red. So we've got a red proton here, and I'll call these ones blue. And what we'll do is practice something from last term, or I guess 2 terms ago. So we've got our eyeball looking through there. So let's draw this in the Newman projection. All right, so if we're looking straight down, what are going to be the legs for this? Yeah, the two red hydrogens, they're going to be the legs in front. What's going to be sticking out on top? A propyl group. So we'll say propyl. Okay. All right, and then let's look at the back carbon. That nitrogen, for the alkylated nitrogen, will that be on the upper right, upper left, or bottom?
Top right.
The top right. So if we're looking this way, it's sticking out, which means it's going to be on our right.
Oh my god, that was fabulous.
The gas leads towards us, correct?
No.
Wait, it does. I mean, that's what I meant wedge. I meant wedge.
You meant wedge.
Okay, so that's going to be over there. Our hydrogen that's not drawn is assumed to be sticking out to into the board. And then below it, we've got a methyl group.
Oh my god, if you could do that more, that'd be great. I don't think you did it.
All right, so let's take a look at it. Which proton is anticoplanar to our leaving group? The one on the left or the right? So we could look at this and we could say this is anticoplanar. All right, let's compare this to the other product. Let's say we're looking down this way.
You have to do a demonstration.
I'll do the demonstration. All right, so we've got our other Newman projection looking down the other alpha-beta bond. So in this case, we've got all three blue hydrogens. All right, is our methyl group going to be on the left or the right?
On our right. Wait a minute. I'm looking. Oh, the methyl group.
It's going to be to our left. We're looking at that nitrogen. We need to fill in the back nitrogen, so we're asking, is that nitrogen with the three methyl groups going to be on the left or the right? And so if we look at it, it's going to be on our left, because if we think about it, this is sticking out, right? So it's going to be like my fist, and then if we look forward, it's going to be on our left. So in this case, we've got NMe3+. We've got a hydrogen over here. And then we've got a butyl group now in that lower position. Okay. Now we have to identify an anticoplanar proton. And we could say, all right, this proton is anticoplanar. All right, now let's look at the stability of each of these. Which one's more stable? The blue one, why?
Because the bigger groups are more spread out. Yeah.
All right, so let's get back into terminology. This is terminology that may be on the ACS. What do we call this interaction between two big groups?
No.
Special name?
Carrot.
Just because you yell something louder doesn't make it more correct.
Steric class.
Starts with a G.
What? Oh, solid
Gauche. Right? Gauche.
Oh my god, we're doing.
So this is... So Gauche interactions are destabilizing, which means this is more stable. So even though the Zaitsev product, if we go up and we look at it, is more thermodynamically stable, kinetically, it's a lot easier to grab the more accessible beta proton, which in this case leads to the Hoffman product. So let's make a little note of the regiochemical observations. So Hoffman, is kinetically favored, even though it's not the thermodynamic product. Even though it isn't the thermodynamic product. Yeah, that's an interesting question. So people have tried this, and they've said, well, if we want our thermodynamic product, can we crank up the heat? That energetic barrier is so high that in this case it's almost never observed. So, yeah, there may be newer ways, but none that I know of, actually. So in this case, you can't use heat to favor the Zaitsev product. You only observe the Hoffman process. All right, so let's do a practice problem. All right, propose a synthesis.
Interesting.
Involves a reaction that was first reaction on the exam.
Oh yeah, that's great.
I'll give you guys a hint too. If we count carbons coming off the phenyl ring, 1, 2, 3. 1, 2, 3, 4.
Sienna.
Yeah, we've got to gain a carbon somehow.
Oh, I didn't do that on the test. See, I know this. Did you see what I'm talking about?
It's
I do know this.
All right, so if we want to add a carbon in, we can do an alkyl or an SN2 substitution.
Can you have test anxiety or something?
All right, but we can't do Hoffman elimination with a cyano group. So what do we need to do?
Reduce it.
Reduce it. So we can do LAH and water. I haven't gone through and graded all of the exams, but a lot of people forgot to add in that extra carbon. It was worth 1 point out of the 3. As long as you got the reduction, it was okay. All right. And then if we want to do our Hoffman elimination, what reagents do we need? For step 1.
Definitely just put that in. Oh, you use methyl iodide.
Methyl iodide in excess.
Elemental.
All right, so we over-alkylate, and then how do we drive it off as a leaving group?
Silver oxide with water.
Yep. And oftentimes they add heat too, just to favor the elimination reaction, because elimination reactions are always favored under high heat.
For the NaCN, it's a halogen reagent should be KCl.
You can use any sort of cyanide salt. They're decent enough nucleophiles to do an SN2 substitution. All right, so now let's switch gears a little bit onto a new reaction. So reactions with nitrous acid. All right, so let's do a little bit of review here, because this is something that even good chemists flip-flop.
When you say flip-flop, you mean like they change their mind?
No, they misstate things.
I don't know where they go.
All right, compound on the left, what do we call that?
Nitric acid.
Nitric acid.
And
Adiicitis, not that hard.
So nitric acid is different from nitrous acid.
oh, this is like Chem 161.
This was easy.
Yeah.
So we do have to pay attention that this isn't the same nitric acid that we've seen with our electrophilic aromatic substitution reactions. All right, just to compare though, if we treat nitric acid with H+, what are we going to get out?
You get that NO2 thing.
Yeah, the nitronium ion. So just like in lab, we reacted nitric acid with sulfuric acid, and we got our nitronium ion. I know you guys know this because I saw in your lab reports you drew the mechanism. What about if we take nitrous acid and we react it with H+? What do you think we're going to get out? It looks really similar, right? We're going to protonate that alcohol and turn it into a good leaving group. And this looks pretty frustrating. So if we look at nitrogen, the octet rule isn't satisfied here, right? This would be something that would make most chemists cringe, but what could maybe happen here? Resonance. So we form something similar, but there's a resonance structure where we can satisfy the octet on that nitrogen. And this is called the nitrosonium ion. That's a good question. In this case, the nitrogen end is much more electrophilic. Because if you think about the electronegativity here, oxygen's really, really unhappy with a positive charge. Nitrogen is less electronegative. It's more okay with a positive charge. All right, so now let's look at the mechanism for making the nitrosonium ion. So it's just like you guys would suspect. In fact, you guys have already seen this before. Do you guys remember when we made Azo Dyes?
Yeah, I like that one.
So with Azo Dyes, what was the salt called that we used?
No idea. That was fun. Wow.
So it's sodium. No, sodium nitrite.
I'm so tired right now.
All right, sodium nitrite. And then in the Azo Dye lab, we reacted this with HCl. We protonated our alcohol. And then if we have more HCl around, we can protonate it again. Okay. So now what can happen? Let's draw in all our lone pairs for this one. This can get shoved off. And then we've got oxygen triple bonded to nitrogen with the lone pair. That oxygen's positive. We also get water. And then we said the resonance form for this involves a double bond to the nitrogen, and the nitrogen has a positive charge. And we said that this is major and this is minor, simply due to the electronegativity difference between oxygen and nitrogen. All right, so let's see some reactions with the nitrosonium ion. It's going to act like a very, very good electrophile. All right, so the first reaction is with primary amines. So let's take a look at what happens when a primary amine reacts. So first thing we do is we take sodium nitrite, we react this with HCl, I didn't show it as equilibrium conditions, but it is, and the equilibrium is actually not that favorable because we're forming a highly unstable intermediate. And even though we aren't producing a huge amount of it in solution, it's still reactive enough to continue on. So if we have an amine around, this amine can do a nucleophilic attack and attack our electrophile, right? So I'm going to flip this around a little bit just to make it easier to draw. And now our nitrogen that added in has a positive charge. What do you think the next step is? Probably want to deprotonate that nitrogen, make it more stable. So water can participate, grab this, stabilize our nitrogen. Okay, and now we've created H3O+. The oxygen will come and grab this proton, kick off water. Okay. Now we've got water around that can act as a base again. And this water will actually come grab this proton, clamp down, and kick up electron density all the way to that positive charge. So it's kind of like a Jacob's ladder. Okay, and then we recreated acid here. And the alcohol can get protonated one more time. And then what do you think happens? Yeah, we can shove off that leaving group. And then if you look at this, we're drawing a cation. What would be the counter anion for this reaction? Let's go and look through our reagents that were all added.
Sodium.
It's got to be an anion. Chloride. So in this case, we used HCl in the beginning. Chloride can count as our counter anion. And this is called a diazonium salt. These are super, super reactive, right? Do you guys remember me telling you in lab you don't want to let these dry out because they tend to be pretty explosive? Why are they explosive?
It wants to be nitrogen gas.
It wants to be nitrogen gas. So these are really good intermediates because you can expel off nitrogen gas. Let's actually go to secondary amines before we talk about the reactions involving diazonium salts. So our example in lab, we used a primary amine. The reaction with secondary amines is actually a little bit different. We still have to make our nitrosonium ion with HCl. But this time we've got a secondary amine. the nitrogen can still attack into our nitrosonium ion. And then if we have water, we can still do this deprotonation. But this time we're kind of stuck. And we're stuck at this product. And this product gets named like an amine. So we have a substituent coming off of our amine. When we have a substituent coming off of an amine, how do we normally name it? Yeah, we have N dash something something, whatever the substituent is. So these are N-nitrosamines, or N-nitrosamines, I guess. These are pretty interesting. In your textbook, it talks about it a little bit. But unfortunately, the people doing studies on N-nitrosamines found out the hard way that they are super carcinogenic. And so typically, we try to avoid making these. Oh. So you read these papers from the early 60s, and unfortunately a lot of the chemists actually died way, way too young because they didn't know what they were making caused horrible diseases. The other thing we found as we've studied public health is that these are found in cigarette smoke. So when people say cigarette smoke causes cancer, we know why. You've got N-nitrosamines in there. The other one that breaks my heart. Fried bacon.
No.
Yeah. So even though we all love bacon, or some of us love bacon, not everybody. Caston's here. You're vegetarian, right? You're vegetarian, though, right? Oh, I thought you were. Oh, okay. My girlfriend's vegetarian. A lot of people are vegetarian. They don't eat bacon. I was just saying not everybody likes fried bacon, but it has N-nitrosamines in there.
What about turkey bacon?
I don't know about turkey bacon. And then a lot of cured meats have N-nitrosamines in there. So if you are a super heavy-duty meat eater, your chance of getting cancer is actually higher than a non-meat eater. It's kind of our penalty we pay for enjoying bacon. Yeah, whether or not it's worth it is a little bit suspect. All right, so let's talk a little bit about reactions of diazonium salts. So alkyl diazonium salts. So let's go ahead and say that I made this guy. We said that this thing really, really, really wants to form nitrogen gas. So if we pop off this and form nitrogen gas, what we end up getting is a carbocation plus N2 gas. Yes, this is the chemical term for saying you cannot control this reaction. You form a secondary carbocation, what do you think might happen? It'll rearrange. What else might happen? Other nucleophiles will add into it. It will start doing anything it can do in order to become more stable. So it essentially turns into a runaway train, and it's never coming back. All right. At least I can make myself laugh. Aryl diazonium salts are different, though. All right, so alkyl diazonium salts are too reactive, but aryl diazonium salts are pretty darn neat.
Now she's singing the song.
All right, with the aryl diazonium salt, you can do all sorts of reactions with it, so I'll get a little chart going. The first thing we can do is we can swap out this for chlorine. So we can install chlorides this way. We can install bromines. We can install iodine. And then the other cool one that's very useful is you can install a cyano group. This is called the Sandmeyer reaction. And in order for the Sandmeyer reaction to work, we have to actually use copper. So in this case, we use copper 1 chloride, or copper 1 bromide, or copper 1 iodide, or copper cyanide. And let's include the reaction name. This is called the Sandmeyer reaction. It's very, very synthetically useful. So theoretically, we could go from an aniline. We can turn that aniline into a diazonium salt, and then we can swap out that aniline for any one of these. And then, specifically, if we choose a cyano group, we can continue doing chemistry on our cyano group. We can turn this into an amine, a carboxylic acid, a whole bunch of other stuff. So these are very, very powerful reagents. The book doesn't show the mechanism, but I wanted to show it to you guys anyways. It's a really short and easy mechanism, but a lot of people tell me I don't like seeing mechanisms that I just have to memorize. I want to understand a little bit of why they work, so this is why I wanted to show you the mechanism.
I actually like that. It helps me understand what's really going on. Much as I hate to admit it. Yeah.
All right, so we've got our diazonium salt. The first step that happens is actually radical cleavage. So we get this aryl radical, and then we get a nitrogen radical. This nitrogen radical can actually react with copper plus. So we've got our copper anion in there. And so what do you think the copper will do in order to make the nitrogen happy?
Give up one.
Yeah, it'll give up an electron, right? So in this case, we end up with and Cu2 plus. How does the first step happen? Radical cleavage in this case is so favored because we're liberating nitrogen gas. That bond is very, very weak. Weak bonds can tend to undergo radical cleavage. In this case,
if you buy a bottle, right?
No, you guys, let's make sure we can hear Eddie. He's saying, why would it break apart and become...
If you were to buy it that way.
So you have to initialize it, and in this case, it's not very favorable without the copper around to stabilize the nitrogen. So this process is a little bit more concerted than I have shown. It's almost happening all at once. The copper is giving the electron to nitrogen at the same time this radical cleavage is happening. So without the copper there, it'll stay put. Okay, so now we've got this aryl radical. So this is part one. Part two says we've got this aryl radical. And then we react this with some sort of halogen. And then we take away an electron. So I'll do minus E plus, and we can get our halogen installed. And what do you think's taking back its electron? Yeah, the copper. So in this case, we reform our copper plus. So this isn't a typical organic mechanism. It involves inorganic chemistry a little bit, some organometallic chemistry, and then redox chemistry as well. So it's kind of this hodgepodge of chemistry, but it's a really cool and powerful tool, primarily because we're driving off nitrogen gas, which turns it into a great leaving group. All right, I think we have one more.
Dr. Kingle, come on.
All right, I'll stop today. No, so tomorrow what we'll do is we'll start using this a little bit in synthesis, but there's a couple other offshoots of a Sandmeyer reaction that are also synthetically useful.